It's good. So, hello everyone. So, it's a work joint with Raphaëlle Crubillé, and it's about the contextual distances in between programs in higher order randomized programming. So, we consider the notion of contextual equivalence between programs. Two programs M and N are going to be equivalent if and only for any context C. We can get the same observation on C of M and C of N. So context model the environments. They are programs in the same language, and each context contains the occurrence of a whole. And when we put a program M in a whole of a context C, we get a program C of M, and the observation is what we can observe from the execution. Here we are in the probabilistic case, and so we can observe the probability of termination with the value 1. So it will be interesting now not only to say that two programs are equivalent or not, but to say that two programs behave in a similar way with a high probability. Here, for example, I have the program M which return 1 with probability 1, and the program N which return 0 with probability epsilon and 1 with probability 1 minus epsilon. So here M and N are not contextually equivalent because I can find a context that separates them. So it will be interesting to say that for a very small epsilon, the two programs M and N are very close. And so the question is how we can generalize the notion of contextual equivalence in order to compare quantitatively two programs M and N. So a direct generalization of this notion of equivalence, we have the notion of contextual distances, which is defined as the supremum over all contexts for the difference between the observations when we put M in the context. But here we have a problem which appear this is what we call the trivialization phenomena. The idea is that these two programs, previously said very close, are with distance 1, and it's because we can construct a family of contexts. For the first instance, we construct C2 that takes two copies of the program and evaluate each copy independently and return 1 if all instances return 1 and 0 otherwise. And so here, when I put M in the context C2, I will have probability 1 for the first program, but for the second program, 1 minus epsilon to the power 2. From each instance, I have 1 minus epsilon. And so if we increase the number of copies, and do the same algorithm, so when N becomes more and more bigger, the probability for the second program becomes more and more smaller. And so the distance between M and N will be equal to 1. So this trivialization phenomenon is formalized by Crubillé and Delago in this theorem. So if we have a probabilistic language in which all programs terminates with probability 1 and the context can copy the arguments. So for any pair of programs M and N, either I have M and N are contextually equivalent and the distance between them is equal to 0, or the two programs are not contextually equivalent and the distance between them equal to 1. So an example of a such language, I have T plus, a probabilistic extension of the Gödel system T with the addition of an operator choice here. This negative result of trivialization is not a blocking result. That means that there is another approach to define contextual distances for which we don't have the trivialization phenomena. For example, we can restrict the number of copies that context can make and define the linear distance, which is defined as the supremum over all linear contexts that use the argument exactly 1 times for the difference between the observations. We can also define a family of a graded distance in which for each N we define the distance as the supremum over the context that copy the argument at most N times for the same difference between observations. Here we don't have the trivialization phenomena, but the trivialization phenomena appear in the limit because the family of a graded distance converges to the trivial metric. And another approach is to work on the first condition on the language and to introduce a divergence divergence programs in the contexts such as the amortized distance defined by Thomas hierarchy. And so here in this work, we provide a new proof of the trivialization phenomena based on a purely probabilistic reasoning. So the original proof of the trivialization by Crubillé and Delague used techniques from real analysis as, such as the Brainstem polynomials. But here we show that a result from probability theory, the law of large numbers, is in the heart of the trivialization phenomena. And so, as consequences, we can use results that refine the law of large numbers, such as the Central Limit Theorem, which study the speed of convergence of the law of large numbers, to study the speed of convergence of the graded of the family of graded distances to the trivial metric, for example. And we can use another results from the law of large numbers and inequalities to find a lower bounds on the other contextual distances. So I will show briefly how we can use the law of large numbers. So if I consider a Boolean program M, which returns 1 with probability 1, and so I can look to the program M as a probability distribution, and I can associate a random variable of law Bernoulli P, which returns 1 with probability P, and so here again I use the same idea. I construct a family of contexts that copy the arguments k times, and I compute the empirical mean of the distribution. So we have k copies of the program, so we have k independent and identically distributed random variables associated to each copy of the program, and we test if this empirical mean belongs to an interval. So until now it's an arbitrary interval. And in observation, when we put a program M in this context, we will obtain the probability of termination in 1 equal to the probability of the empirical mean belong to the interval. And so here, the importance of the law of large numbers. The law of large numbers state that the empirical mean of a distribution converges to the expected value of the distribution. And so here, if we have the expected value of the program belong to the interval, we will obtain probability 1. And if the expected value is outside the interval, we will obtain probability 0. And so for two programs, M and N, here we have a graphical illustration. If we consider a program M with expected value P and program N with expected value Q, different expected values, so here M and N are not contextually equivalent. And so if I choose the interval around the expected value of the first program and the expected value, and in a way such that the expected value of the second program is outside the interval, so if I increase the number of copies here, so from an order k, I will obtain the probability of empirical mean in the interval for the first program will be equal to 1, but for the second program it will be equal to 0. And this is for the Boolean case, but you can switch easily to the general case using the if-then-else constructions. So for the future works, so we have a few inequalities that come from the law of large numbers. So we have a few lower bounds that we can find for the other distances, and so it will be important to compare the lower bounds in order to define which is the best lower bound on the distance. And we have also the idea to construct a new connection between theories, between the trivialization phenomena and the threshold function theory. And again, we have inequalities that come from threshold function theory that we can use to derive lower bounds. And that's it. Thank you.
Thanks. Are there any questions? Time for one or two.
Thanks. Yeah, so you said something about introducing divergence breaks the trivialization result.
When we introduce the divergence, okay, in a language that include divergence, we don't have the trivialization phenomena, but you will mean the distance, the amortized distance, or in a general language?
Why don't you have? Yeah, why not?
When you have divergence?
When we have divergence, so for example, if I construct the context and with an operator choice, okay, with a divergence, with a choice between the divergence and the argument. So in each time I will use the argument, I will pay a cost in terms of probability for the divergence. And so the family of amplification contexts will not give the trivialization, because we don't have we have a term that converges to 1, a term that converges to 0, and so.
Okay, interesting. Thanks.
Thank you.
Okay, let's thank the speaker again.